Hi, my name is David Corish, a PhD student in Trinity College Dublin. My research investigates the cellular response to nanoscale titanium surfaces, with the goal of this project being the design of novel implant surfaces which can be applied to medical devices and bone and tooth implants. Take a tooth implant for example. Once inserted into the jawbone, you want the body to respond with quick healing, no infection, and a rapid fixation of bone to the implant with a strong, long-lasting bond. To understand how the body response affects the implant success, we must first look at the cellular response. Cells are the building blocks of the body, so the response of different cell types to an implant is crucial to the overall success. Imagine you could design a cell-specific material, a material that would encourage the adhesion and growth of a desired cell type, but would discourage unwanted cells from growing in that same region. This could be applied for tooth and bone implants. Imagine if you insert a tooth implant is inserted into the patient. It is exposed to different cell types such as soft tissue cells and hard tissue cells. So if you could design a material that would encourage a specific cell type to respond to a certain region, like bone cells to grow on the bottom of the implant, whilst the soft tissue cells will migrate away and only grow on the top region. Cellular behaviour is known to be influenced by the cell's surrounding environment and its properties. Just like we use touch to detect the physical properties of a surface or its texture, we can tell if it's smooth or soft. We detect the chemical or ingredients of a surface using taste. We can detect the mechanical properties if something is soft or stiff, like we can tell if we're walking on soft sand or solid concrete. Cells similarly can detect and respond to the surface physical, chemical and mechanical properties. In my research, I wanted to know how bone cells responded to these various surface modifications. What makes a bone cell happy on a surface? I used nanoscale titanium surfaces. These surfaces have features in the nanometer range. A nanometer is 1/1,000,000th of a millimeter. Now to put this in context, let's scale up. Let's imagine the distance from Germany to Dublin was 1 millimeter in length. Then 1 nanometer will be represented by this size. That's extremely small. So small it can't be seen using conventional light microscopy. So we have a surface with nanoscale features, but we can't actually see it using conventional light microscopy. Instead, we use atomic force microscopy to essentially feel the surface topography and obtain a three-dimensional surface profile. Confocal and scanning electron microscopy allowed us to image the surface and how cells interacted with that surface. In my research, I isolated surface properties, changing some chemical properties, changing how soft or stiff the surface was, and also its physical topography from smooth to a nano surface. I investigated which properties cells preferred to attach to, which properties cells preferred to grow on. A combination of these properties provided a much better and improved surface for encouraging bone cell growth. This research builds upon the knowledge of how cells respond to various surface properties. The ability to control the behaviour of specific cell types would pave the way to the design of cell-specific surfaces and open up endless possibilities for biomaterials and medical devices.